Hello and welcome. This is the Chapter 2 introduction. Chapter 2 is about atoms, molecules, and ions. Within this chapter, we'll go through a little bit of a description of how we've come to know about atoms and some of their subatomic particles. We'll talk about molecules. We'll talk about ionic compounds as well and get into a discussion of ions. Towards the end of the chapter, we'll go through a systematic approach for naming a few different types of compounds. So a quick overview of Chapter 2. The first section gets into atomic theory of matter. We'll talk about something called Dalton's atomic theory. Then we get into the discovery of the structure of the atom and some of the fundamental experiments that have gone into sort of paving the road for what we know about atoms. We'll talk about modern atomic structure. This will get into the nucleus versus the electrons and how the protons and neutrons reside within the nucleus, something I'm sure you've all heard about before. We'll talk about atomic weights. In the periodic table, we'll then get into looking at some descriptions of molecules and molecular compounds before we get into a discussion of ions and ionic compounds, and then wrapping up with a discussion of how we might name some broad classes of compounds. So Dalton's atomic theory, he really, the early 1800s started paving the way for the discussion or the theory that matter is made up of small individual atoms, and then the different atoms were sort of representative of different types of elements. So you might have things like oxygen and nitrogen, where the atoms of those two different elements are fundamentally different from each other in some way. At this time, we didn't know about protons and neutrons and electrons yet. So we really didn't quite know what made oxygen different from nitrogen, just that there were two different types of elements. One that you might think of as oxygen, one that you might think of as nitrogen, and that generally that these atoms, were the same or thought to be the same with respect to the different elements. We now know that most elements have different isotopes, so within the same element today, you might think of there being different types of atoms within that same element where they're almost the same. They have a small little difference in the terms of their neutron count. We'll get into that description of isotopes as we go along in the chapter. But at the time, it was kind of like, okay, you have oxygen, you have nitrogen. They're two different types of elements. Each atoms are mostly the same within those elements. And then that the elements could not be interchanged with each other. You couldn't just turn oxygen into nitrogen. Nitrogen couldn't become oxygen by some sort of ordinary chemical reaction. But then you could take different elements, mix them together, and form different types of compounds. And so depending on the conditions for maybe how you mix elements, you might get maybe a compound like NO or a compound like NO2, a compound like N2O. Then you also start to get into the finding that compounds would have a specific ratio of the atoms of the element, like 1N for 1O, or maybe 2Ns for every 1O, that you had this sort of law of constant composition, that if you had a compound, say N2O, that the compound always had two nitrogens for every one oxygen. So you had this sort of constant ratio that you would find for the elements within their compounds. So how we came to know about protons, neutrons, and electrons begins with the cathode ray tube experiment by J.J. Thomson. Sort of in the late 1800s, early 1900s is when this work began to be accomplished. Here, a cathode ray, you might think of this as the old style TVs, or maybe you remember seeing some of the bigger monitors for computers when you were a kid. What those were, they sort of involved taking a high voltage of electricity across matter, and it would give off a particle. The particle was later determined to be the electron, but when that electron would fly and strike a screen, it could light the screen up. And so this was like the fundamental basis for how TVs used to work before the LCDs and LED TVs sort of took over the market. But within this experiment, what was actually being done was, at the time, the atom was thought to be the most divisible form of matter. But here, what you could find is that the atom itself contained, small subatomic particles, one of them being this negatively charged electron. Now, the way you find that the electron's negatively charged is that you can sort of flow the negative particles towards the positive direction of an electric field, or you could take sort of a wand, if you will, and move that sort of field of electrons around. So that you can find that the particles themselves are negative in charge. And so then this is another description of the cathode ray tube experiment. So we're sort of taking a high voltage across a stream of a gas, or I think actually a metal is struck with this charge, and then it gives off this particle that then sort of flies towards a fluorescent screen. The screen has a small charge perhaps applied to it to attract those negative particles towards maybe the positive part of the field on the screen. And then you could have electrically charged plates, so you can sort of see how you can bend this magnetic field. You can bend it down towards the positive direction of an electric field. And so this is just paving the way for the understanding of this particle being negative in charge. So you have these negative little particles flowing through this beam that you could sort of interact with a positive electric field. So then the actual mass of the electron was determined through the Millikan Oil-Drop Experiment. So a somewhat similar type procedure to generate the actual particles was undertaken by taking like oil droplets and sort of vaporizing those particles. This actually is atomizing your oil droplets. You have individual atoms, so think mostly carbon and hydrogen, and then you intersect those with a high energy source like an X-ray. And so then that X-ray, what it can do is attach a charge to the oil droplets. And so then the oil droplets would contain a charge that had a multiple number of electrons. So maybe one particle has an electron attached to it. Maybe another particle ends up with 2 electrons attached to it. And so what they could find is by varying the charge on electric field and the ability to sort of see these oil droplets, you could sort of suspend or change where the oil droplets, the rate that they were falling, because they're just falling as a basis of gravity. But then by applying a negative charge, you could sort of like repel the particles back upwards. And that what they found is that, you know, you could determine how many electrons were attached, and then from that and the previous work, it doesn't matter mathematically, we're not really trying to solve how they actually accomplished the arithmetic here, but what they could do is take the finding from J.J. Thomson's experiment, which actually found a mass to charge ratio for the electron. This is able to attach sort of the actual and establish the actual charge and the mass of the electron. Now what this found, or was able to definitively support, is that the electron was subatomic, so smaller than the smallest known atom of hydrogen at the time. And then also what they could do is support that the actual charge of the electron was a particular number of coulombs, and it worked out to be about 1.6 times 10 to the minus 19 coulombs in terms of the charge of the electron, and that it's negatively charged. So then the nucleus was discovered almost by accident by Ernest Rutherford. What Rutherford did was he took a thin foil of gold, and then he shot something called an alpha particle. We'll talk later about what alpha particles are. They turn out to be like a helium nucleus. So they turn out to be the nucleus of a helium atom, which is given off by some forms of decaying matter. And so you take an alpha particle, shoot it at gold foil. This is like shooting like almost like a rocket at a tissue. Okay, so what you would probably expect if you shot, say, a bullet at a thin piece of tissue paper is that the whole bullet would go straight through, right? You wouldn't expect a little tiny tissue paper to be able to tear apart, you know, a big bullet. Well, what they found is that this thin piece of gold wasn't, the particle that we're shooting at this gold foil didn't completely go straight through. It actually is being deflected by the gold foil. And what this actually suggested is that there must be tiny little compact nuclei within the matter, and that every time a particle strikes one of those nuclei, it deflects off of it. Now, there's the nuclei are so compact that the odds are pretty high for the particle still making its way through. So a majority of the particles do end up going straight through, but a lot of them are scattered along the way. So the scattering ended up being sort of indicative of the nuclear model of the atom. The other model, we'll talk about this in a slide later, another model kind of thought that all the subatomic particles might distribute within the atom itself. So if you had all the particles distributing within the atom itself, then you might have expected there to not be this compact nucleus to lead to any scattering, and that most of the particles may have ended up going straight through the gold foil. So this kind of paved the way for most of those particles accumulating within the nucleus, and then only the small, tiny little electrons orbiting on the outside of the nucleus. And that's what we know the atom to be and what you've learned about ever since you were in school. So the nuclear model, we have within the nucleus, we have our protons and our neutrons. These are relatively massive particles. These carry a majority of the mass of the atom. And then the electrons are orbiting outside the nucleus, spinning around, and we'll learn the different types of orbitals that they tend to reside in when we get to chapter 6. So Rutherford postulated a very small, dense, positively charged center with the electrons traveling around the outside. What's noteworthy is that the protons contain a positive charge, the neutrons a neutral charge, and that the proton's charge are opposite that of the electron exactly. So 1.6 times 10 to the minus 19 coulombs. So if you imagine having a nucleus that's uncharged, or excuse me, if you imagine having an atom that's uncharged, then we have to have an equal number of electrons. So say we have 6 electrons, 6 protons within our atom. That turns out to be a carbon atom with 0 charge, because we have an equal number of negative and positive particles, each with the same amount of charge, just opposite of each other. So most of the atom space turns out to be empty, or you can think of it as being empty, with these negatively charged particles being the electron. Now, they repel each other quite well, so if you put 2 atoms next to each other, those electron repulsions are going to keep the atoms from overlapping into this so-called empty space. So most of the atom is space, but it's filled up with these tiny little electrons that will repel each other to a very strong extent, preventing the nuclei of 2 different, say, carbon atoms from touching. So we have 2 carbon atoms side by side. They're not going to directly come in contact with each other due to the repulsion of all those electrons that they contain surrounding the nucleus. So the atoms are small, talking 1 to 5 angstrom. That's 100 to 500 picometers. An angstrom is 10 to the minus 10 meters. So 1 angstrom is 10 to the minus 10 meters. So you're talking 1 to 5 times 10 to the minus 10 meters in terms of their size, in terms of the sort of diameters of these atoms all the way across, accounting for the electrons in this space they occupy. So other subatomic particles, protons, neutrons, are found in the nucleus. Okay, so here's a bit of a summary on our subatomic particles. Our protons contain a mass of about 1 AMU, atomic mass units. We'll talk a little bit later about what the atomic mass unit is. The neutron has almost the same mass, a little bit different, but about 1 AMU as well. The electron mass, very, very small. So you see that a majority of the mass is coming from the proton and the neutron within the atom. So if we go back to carbon, the most abundant nucleus of carbon turns out to be carbon-12. We'll have a slide in a moment that shows that this is our mass number. Now the mass number is the sum of the protons and the neutrons. So the protons and the neutrons added together, that this is our mass number, because that's where a majority of the mass is coming from the atom. This 6 here is referring to the specific atom. That's our number of protons. The protons, the positive particles, are what really make our nuclei different. So if we have nitrogen, it turns out nitrogen has 7 protons in its nucleus. So if you manage to add a proton to the atom of carbon, which is not easy to do, it's not something ordinarily you're going to accomplish, say, in a chemistry lab, but if you were to do that, you would actually change the nature of that carbon and turn it into a nitrogen atom. And so the proton count is given as what we call the atomic number. So the number of protons is equal to the atomic number, because the atomic number is telling you what atom you actually have. And then the electrons are just keeping everything in balance in terms of the charge. So if we have 6 protons, 6 neutrons, 0 charge, then we have an equal number of protons and electrons. Okay, and so then what you can see, or one of the things I wanted to mention, is that this actual atom of carbon would have a mass of 12 AMU exactly. We'll talk later about why that's the case. But the 6 protons, 6 neutrons, 6 electron atom of carbon, exactly 12 AMU. Notice that that doesn't work out if you take 6 times the number of protons, 6 times the number of neutrons. The reason why is these are the resting masses of these particles when they're not within an atom. When these particles are held within an atom, they're actually stabilized by being part of the atom. You actually have some energy due to the stabilization of those particles together. The difference, if you were to add up the mass of the subatomic particles within the nucleus compared to the actual mass of the nucleus, has to do with the nuclear stability. Nothing we're going to calculate here in Chapter 2, but that's an idea you come back to in Chapter 21. Later, we start talking about how stable is one nucleus compared to some other type of nucleus. You can sort of compare the subatomic particle masses versus the actual particle mass to get a sense of that stabilization energy. Okay, so now this is summarizing what we're talking about in the previous slide. The mass number is the number of protons plus neutrons, because those are the particles that carry a majority of the mass of the atom. The atomic number is just the proton count. The positive charge of the nucleus is really what gives it its properties. That if you add another neutron and you have, say, a carbon-13 atom, the difference here is you have 7 neutrons, still 6 protons. If you had 7 protons, it would be nitrogen. So an isotope just varies in the number of neutrons. The neutral particle doesn't really change the property of that atom by very much at all. In fact, it mostly behaves just as the exact same type of atom as the carbon-12 atom. Now, it turns out the carbon-12 is about 99% abundant in terms of all the carbon in a natural sample. Carbon-13 accounts for about the other 1% of carbon. Carbon-14 There's a small amount of carbon that has 8 neutrons within a natural sample, but this is less than 10 to the minus 10%. You can still actually date a sample based on how much carbon-14 it contains. Again, another topic out of chapter 21. We're not going to go through dating samples here in chapter 2, but even though the percentage of carbon-14 is really low, it still turns out to be a pretty important isotope of carbon. So moving on to isotopes, this chart here is just kind of comparing some different isotopes of carbon. Carbon-11 would have 5 neutrons, carbon-12, 6, carbon-13 would have 7 neutrons, and then carbon-14, 8 neutrons. Now, we're not going to find any carbon-11 in a natural sample. Again, 99% is carbon-12. It turns out you don't have to memorize these numbers. About 1% is carbon-13, and less than 10 to the minus 10%, just a very tiny trace, is carbon-14. Now, most of the other elements in the periodic table have a similar set of isotopes that they exist as. Some elements do exist just as one isotope. So it's not the case that every atom exists as multiple isotopes. Some, like iodine, actually exists as just one isotope in its most predominant case. So now, it's useful for us to think about atomic weights for elements in one part because if we look at a periodic table, we see masses listed underneath each of the elements. It'd be good to know what those masses are really representing. What they're representing are the average atomic weight for an element. These are what we see listed on a periodic table. And we'll see in chapter 3 that these are really useful for doing problems with, because when we start doing problems where we're calculating having like several grams of a substance, we really want to think on average. What's the average atomic weight for an element considering all the sort of isotopes that it commonly exists as in a natural sample here on Earth? So what we would do is we would sum over all the isotopes for a given element where we take the isotopic mass times the fractional abundance of that particular isotope. So if we look at carbon as our example, because we did this example in the previous slide, so it turns out carbon-12 has that mass of exactly 12 AMU. Carbon-13, we'll do a problem later where we summarize this. It's about 13 AMU, but it's not dead on 13 AMU like carbon-12 is, exactly 12 AMUs. But so if we're doing a rough calculation for the average atomic weight of carbon, what we would do is say, okay, 99% of carbon, so representing that as a fraction, 0.99 is carbon-12, and then 0.01, about 1%, is carbon-13. So if we carry out this math here, I'm going to do it real quick. I'm guessing this is going to come out to be about 12.01. So it's going to be really close on average to the mass of carbon-12 because that's where our abundance lies. So 12 times 0.99 plus 0.01 times 13 works out to be 12.01. Now we do have a bit of a sig fig issue. I don't want to turn this into a sig fig problem. But if you look at a periodic table, underneath carbon you probably see 12.011 or 12.0107 or maybe even more precise than that. We can get greater precision if we include slightly more precise masses here and abundances. We can work this out to a greater precision, but you're kind of seeing that what we might want to list for carbon is, well, what is the average? If we had an average atom of carbon, what would its mass be? The mass of the atom would either be 12 or 13, but on average, what we do is take a weighted average for all the isotopes that exist naturally for that particular element. Okay, so our periodic table is organized from left to right by increasing number of protons in the nucleus of the atom, so 1 proton for hydrogen, 2 for helium, but then grouped into similar trends of particles from top to bottom. So our alkali metals, we know that these all form plus-charged cations commonly in nature. The noble gases exist as stable elements. They exist as gases at room temperature, so helium exists as a gas, neon as a gas. Now F2, these tend to form minus charged ions, and what you kind of see is that the electron count of these atoms are trying to go towards what they are for the noble gases. So if you look at neon, neon would have 10 protons in its nucleus, and uncharged would have 10 electrons. So if you look at fluorine without a charge, it would have 9 protons, 9 electrons. For an uncharged atom, have an equal number of protons and electrons. Now, if we gain an electron, pick one up, then we go to have still 9 protons. Not easy to change a proton count, but the electrons are small. On the outside part of the atom, we can pick up an electron from fluorine if we have something to give it an electron, maybe something like sodium. So maybe sodium goes from having 11 protons, 11 electrons as sodium with a 0 charge. But if we add a plus charge to sodium, we now have 11 protons, 1 fewer electron. And then maybe that electron has gone over to fluorine, something like maybe F, where we have something maybe like NaF form, where we have this ionic compound form between sodium and the fluoride ion. So notice that sodium and fluorine are forming these common ions where they have the same electron count as that noble gas. So there's really something special about having 10 electrons, it turns out. We'll talk about electron diagrams and talk about ways of picturing orbitals and things like that, and sort of looking at sort of a picture of why neon is so stable in terms of its electron configuration when we get to chapter 6. But at this point here, we can kind of get an appreciation that the atoms on the left side of the periodic table want to lose electrons more readily, and the atoms on the right side of the periodic table want to gain electrons more readily. Notice that these are our non-metallic elements over on this side here, so these are our nonmetals plus hydrogen, and then our metals are all the elements, a majority of the elements, on the left side of the periodic table. So the metals want to lose electrons more predominantly. It's easier for them to do that compared to gaining electrons, which is easier done by the atoms on the right side of the periodic table. So now our key groups, alkalis. The alkalines, the next group, like magnesium, calcium, strontium, barium. The chalcogen group is the oxygen group, so oxygen, sulfur, selenium are our key elements there. Halogen group, fluorine, chlorine, bromine, iodine, the most common ones, and the noble gases. So these are the 5 groups I would recognize by name on the periodic table. Okay, now as we start thinking of formulas, the thing that really makes a molecule special is its formula. What really makes it special is how the atoms are arranged and how they're connected together. We'll get into some of that information in chapters 8 and 9. But H2, 2 hydrogens fuse together, O2, 2 oxygen atoms, H2O, 2 hydrogens and an oxygen. Hydrogen peroxide has 2 hydrogens connected to 2 different oxygen atoms. CO, carbon monoxide, harmful, dangerous compound, can kill you. Carbon dioxide, well, it can too, but not as readily as something like carbon monoxide will. You're going to be really careful heading to winter fueling season. If your apartment or your home has a natural gas or some sort of propane style heater, change your air filter. If you don't change your air filter, you might be forming carbon monoxide. We'll talk about a little bit later in chapter 3 about why that might be the case. We also have compounds like methane, CH4, ethylene, C2H4, ethane would be C2H6. So C2H6 would be CH3, CH3. We're going to get into naming things like methane, ethane, naming these sort of things that we call binary compounds like carbon dioxide. Binaries contain 2 elements in any proportion, but not 3 elements. So precisely 2 elements in any proportion is what we call a binary compound. And we'll also learn how to name a bunch of ionic compounds. So mentioning ionic compounds, these are things like NaCl, generally formed between metals and nonmetals, because metals can more easily lose electrons, nonmetals can more easily gain electrons. So sodium loses an electron, goes down to 10 electrons like we talked about previously. Now chlorine is like fluorine, except that it's closer to argon in terms of the periodic table. So chlorine has 17 protons and 17 electrons in a neutral atom. If it picks up that electron lost by sodium, then it goes up to 18 electrons, the same count as argon. So argon has 18 electrons. And so then you get this plus, actually that's the minus, but you get this alternating charge here of the minus charge plus minus plus in terms of a lattice where you have just millions of these ions existing together where you never really have the existence of a single NaCl unit like a molecule. So it really doesn't exist as a molecule, but really as these individual repeating ions in nature. Now, when we start thinking of formulas, we can express formulas as an empirical formula. That's the simplest whole number ratio of the atoms or the ions in a compound. This is most useful to describe an ionic compound. So an ionic compound, it's really, what we're really saying is the empirical relationship of chlorine and sodium is just 1 to 1. So that's what's really important for sodium chloride. Now, what's really important for a molecular compound is for us to give the specific formula. So like H2O2 is a molecular formula of H2O2 for hydrogen peroxide. If we were to say HO is the empirical formula, that's true, that is its empirical formula, but it really doesn't tell us much about the molecule itself. What tells us about the molecule is the formula and then its molecular structure. And we'll get into those structure details later in chapters 8 and 9. So if we know the molecular formula of a compound, we can determine its empirical formula, but the converse actually isn't true. If all we know about hydrogen peroxide is the empirical formula is HO, we wouldn't necessarily be able to determine the molecular formula from that information. This is kind of alluding to something from chapter 3. Later, what we'll go through is experimentally how we can find an empirical formula for a random compound, and then do a second experiment where we find the molecular weight, which helps us establish the molecular formula. So our ions here we're seeing our alkali group form plus charged ions, the alkaline group plus 2 ions. Transition metals, these form a variety of charge states, so it's hard to predict these states. We'll talk about those later. And then we tend to form minus ones in the case of hydrogen, fluoride, chloride, bromide, iodide, minus 2 in the case of oxygen, sulfur, selenium, tellurium, minus 3 in the case of nitrogen, maybe even phosphorus in terms of its group. So you're seeing some periodic behavior in the sort of columns of the periodic table that are behaving with similar trends. Hydrogen also forms a plus 1 ion like the alkalis. Now remember, hydrogen is not a metal, so it's not an alkali metal, that the metallic elements are called the alkali metals within that particular group, and they share more trends together. And so our cations, those are the positive particles after they've lost an electron. The anions are the negative particles once they've gained an electron. Our polyatomic ions are representing groups of atoms that have paired up together where there's still an overall charge in the unit. A common example is NH4, where we have 4 hydrogens. We'll talk later about the specific geometry, but 4 hydrogens attached where we have an overall positive charge. So sometimes we might express this charge like this way here. So instead of writing the charge on the nitrogen atom, maybe we write the charge here. Now, the ammonium cation could be attracted to things like the chloride ion, so maybe we'll have a compound like NH4Cl, ammonium chloride. You could also pair it up with another molecular anion like sulfate ion. So sulfate is SO4 2- with the 2- charge. Now that's the nature of sulfur and oxygen. You know, we just have to sort of start memorizing that sulfur with 4 oxygens and a 2- charge is sulfate. The only other type of ion that sulfur forms is SO3 2-. So once you kind of learn that 2- is the charge, then you can exchange the oxygen count. And then if you do, then we end up having a systematic way for naming this compound here with 1 fewer oxygen as sulfite. So you lose an oxygen off something you know is it has an ATE suffix. The new suffix has an ITE suffix. If you gain an oxygen, now sulfur doesn't actually form this compound, but you don't need to know what forms it doesn't form. You just need to know how to name things that exist. SO5 2-, if we had that compound, we would call that per-sulfate. And then if you lost another O, say you had SO2 2-, then you would call that hyposulfite. Okay, so we're going to come up with these systematic ways of naming. This is just giving us an introduction in terms of the spanning of, you know, for a given anion, we might have a spread of 4 different anions that we would have to know how to name, where really we're just sort of memorizing, okay, for sulfate, let's just memorize 4 and 2-. 4 oxygens, 2- charge. Then if I drop an O, keep the charge, it's sulfite. Drop another O, keep the charge, it's hyposulfite. Add an O to sulfate, then it's SO5, still with the 2- charge for per-sulfate. Now, as we write formulas for compounds, a compound should be overall charge neutral. We have to have a balance of the plus and minus charge. So magnesium nitride, if I was to say, okay, you have a compound, magnesium nitride, what we'll learn is that for ionic compounds, you just need to give the cation, then the anion name. You don't need to put these subscripts into the name because magnesium, well, that's interpreted as an alkaline member to be have a 2+ charge. Nitrogen's group forms a common ion with a 3- charge, and we got to pair these up. So if I have 3 magnesiums, 2 nitrogens, and I have a 6+ from the positives and a 6- from the negatives, so the formula would be magnesium nitride Mg3N2. So I don't need to call this trimagnesium dinitride or anything. I don't need to incorporate these names because the understanding of the nature of the charges tells me the proper formula for those anions. So if I was to do another example where I said, okay, imagine you have something like potassium sulfate. Then you would know sulfate is SO4 2-, potassium is K+, so this would be K2 SO4 to balance it out. So pretty simple once you get the hang of it and once you learn a few different anions' names. So the basic nomenclature we'll go through in this chapter are things like ionic compounds, plus-minus compounds, so metal and nonmetals, and then we could have things like ammonium. That's just about the only molecular ion we'll learn how to name in terms of the cation, but there'll be a bunch of molecular anions that we have to learn. We'll go through some of those later. We have to then learn acids. An acid is just where you imagine having an anion, and then you sort of pair it up with hydrogen. And then this isn't an ionic compound, it's something better characterized. I keep missing the L in the chlorine, so let me start over. So we have HCl, we have things like maybe HClO3, and then HClO4. Now for HClO3, the name of this compound is chlorate. That's something we'll memorize later and we'll point that out. Of course, Cl- is chloride. So the name of HCl, you probably know that it's hydrochloric acid. HClO3 is just chloric acid. So if you see the hydro out in front, then you know that's the simple case where you just have one single anion with a charge indicative of where it lies in the periodic table, and then the proper number of H's to balance it out. So now we have an H plus Cl minus, but it's really not like NaCl, where the H plus, when we actually have the compound here, we actually do form a molecule of HCl, where this exists as a single intact molecule, can exist as a gaseous particle, it turns out, unlike NaCl. Now HClO3, different molecule, different formula, should have a different name. The same as chloric acid. Now we added an O, that would be perchlorate. So ClO4 would be have the per out in front for perchlorate. So HClO4 is perchloric acid. So perchloric acid. And now if you go to HClO2, I keep forgetting the L and the H on the chlorine. So if we have HClO2, we want to name that compound, its systematic name will be us. So it'll be chlor OUS acid. And if you have HClO, that would be hypochlorous acid. So we'll pick up this systematic nomenclature system for acids so that we basically memorize something like ClO3 minus is chlorate. So 3 oxygens with a minus is that 8 for chlorine. That's its common representative oxyanion. And if you add an O but keep the charge the same, that's per. If you take an O away, that's ite. Take a second O away, that's hypoite. And then you can sort of pick up these acid nomenclature systems, which just kind of go hand in hand with whatever that base anion is underneath that acid. So binary molecular compounds, these are molecular compounds, so still no metals present. These are things like SO2, N2O, carbon monoxide, carbon dioxide, like we mentioned earlier. So 2 elements, but in any proportion. We can start naming those. We're going to have to pick up the dis and the tris. So like sulfur dioxide, dinitrogen monoxide for N2O. And then we'll also name some simple alkanes like methane, ethane, propane. Bit of a reason why what we're doing is we're just basically adding a CH3 group onto methane, adding another CH3 group, and we're sort of keeping 4 bonds of carbon. We'll pick up some of the structural details of these compounds a little bit later when we get into the more in-depth lecture on this topic. And then the alcohols are just replacing an H with an OH group in one of the cases. So we remove like an H, replace it with an OH. Now that's the alcohol. So that would be methanol. Ethanol is C2H5OH, and then propanol will be C3H7OH. So very systematic in terms of the way we'll name things here in Chapter 2. It'll just be sort of picking up the system and hopefully naming some things from that system. So a couple of problems to wrap up. We kind of did this problem earlier, so I think I'll gloss through this one here. Here what we're being given is slightly more precise abundance of that carbon-12 atom. Still the mass is exactly 12 AMUs, and then 1.0% is the abundance of carbon-13, more specific atomic mass given. The carbon-14 mass is so small it's not going to contribute, so can we calculate the average atomic weight of carbon? So this is just 0.9893 for the 1 carbon, multiplied by 12 AMU exactly, and then we're going to add that to the 0.107 abundance for the carbon-13 times the mass of carbon-13. So with this problem here, you can actually a bit more precisely work out the sig figs. Like we're going to keep all 4 sig figs. This is an exact number, so we don't track that as 2 sig figs. That's like an infinite number of sig figs. So this just gives us like the sig fig balance for what we were working out earlier. So 0.9893 times 12 exactly works out to 11.87. All 4 digits there being significant. If I carry a couple extra, 16 AMU, and then plus 0.0107 times 13.0034. That works out to be 0.13913. This being good to the 3 significant figures. And so then we add them together. and do the arithmetic, we get 12.01 AMU, or we're just seeing the sig figs work. So if you go even more precise, you can get even greater precision onto this to see what's listed on the periodic table. But just a quick way of using that average atomic weight is just the sum of the fraction of a particular isotope times the atomic weight of that particular isotope summed over all isotopes. So here's that expressed maybe in a formula in a slightly more useful way than that equation was written out earlier. Okay, then one last problem to wrap up. Name the compounds Na, NO3, so plus minus. Now, sodium's in the alkali group. That's how I know it's a plus. So that helps me figure out the NO3 has to be a minus. And so this turns out to be the 8. So that's sodium nitrate. So let's say now, given that NO3 minus is nitrate, that helps us know that, we don't really have to know much to know that NaNO2 must be sodium nitrite. Okay? Now, it turns out NaNO doesn't really exist, but we're not trying to quiz you on what does or doesn't exist. We're just trying to, get you to understand if we give you a formula, you should be able to name things systematically. And you don't have to predict whether or not these things exist. It turns out there is no NaNO4, there is no sodium pernitrate. But again, not something we expect you to know that they don't exist, but rather that if it did, you should be able to systematically name that substance. HNO3, well, that's the 8 underlying ions, so that would be nitric acid. HNO2, that would be nitrous acid. And then we have methane. Probably knew that already, and then this is just simply methanol. So we'll go through a little bit more of a description of naming things later and go through plenty of examples in class. So that's our rough introduction, or a relatively quick introduction. I made this a little bit longer than maybe I originally planned, but I think this gives you a good vantage point for what Chapter 2 is all about, so that we can kind of start Chapter 2, meander our way through it, see a ton of examples, and then make some progress in class, and then move forward into a slightly longer summary video later. And then hopefully along the way, we're working on quizzes, practice problems, homework sets, and just making sure we get to the point where we can solve problems like naming, solve problems like average atomic weight problems, answer questions about the nature of proton, neutron, electron counts with ease and poise. All right, guys, that's all for this video. Thanks for the attention.